This video is to demonstrate the capabilities and speed of a novel support generation algorithm that I've come up with for SLA 3D printing. Currently, automatically the support generation is done when the model is loaded in. And there are some stats at the bottom of the screen here. So this model has 10,050 triangles, and support generation took just about 156 milliseconds. Since supports are already generated, I'm going to toggle them on. And we can see now that the supports show up as pillars. Currently they're programmed in as lines, but pretty easily they could be converted to geometry like cylinders, triangles. A friend of mine suggested that kind of barrel of monkeys game, and I actually considered that for a second. But anyway, that's kind of beside the point. So the nice thing about this is that the support is generated so fast that you can translate and rotate and scale the model in real time and see the updated support generated within a few seconds at most and a few milliseconds at least. So if we if we translate the model in the z-axis down by 40 millimeters, we see here the support generation took 128 milliseconds roughly. Some of the things that this takes into account are the pretty standard features. The supports are model aware, so they don't collide with the model. The supports take into account the unsupported area, so they don't get too close to each other. And they also take into account the angle of each triangle that they're supporting. So there's not support on vertical faces, there's not support on faces that don't need it. So now let's demonstrate that by rotating the model. So I'm going to rotate it about the x-axis by 12.8 degrees, 22.7 degrees in the y, and 15 degrees in the z-axis. And so I'm going to click rotate, and then almost instantly, about 103 milliseconds, the support was regenerated. So here we can really see a demonstration of the support being model aware. It contacts the model there and there as well, but doesn't actually pass through it. And the same thing can be seen here. There were support pillars there before, but they were much shorter. And now that there's more room for them before they collide with the model, they take up that room. Additionally, from the back side here, we can see that the support is not very densely packed, so it's in fact taking into account the unsupported area, making sure that there's not too much support material, but the model is still supported well enough. One of the potential applications of this is with the speed of this, it's actually now possible to calculate the support at various orientations that the model can be printed at, and then find the minimum amount of material used to save money or to save time on the printing, or just to save material for the environmental impact. Moving on to a more complicated model, this is the Stanford Bunny, the 3D scan. I downloaded it from Thingiverse. It was uploaded by MakerBot. The number of triangles in the model is a little over 112,000, and loading it in support generation took a little over 5.3 seconds. So this usually is the worst case, where there's a flat plane like this that's parallel to the XY plane. If we rotate the model though, let's say we rotate it 32 degrees about Z, 25.4 about X, and 18 about Y, it should only take a few seconds to regenerate the new support. So yeah, here it took 2.92 seconds, which is substantially less than the 5 or 6 seconds that it took originally. And if we zoom in, we can see support structures are still model aware. They still stop at the model and don't pass through it. They still are taking into account the unsupported area. They're not too densely packed. And they're still taking into account the triangle angles relative to the XY plane. So that's pretty standard, of course, for support generation algorithms, but really the feature that we're focusing on is the speed of it. The speed also applies if we scale the model. So if we scale this to 75% scale, within a few seconds, 2.58, 2.59 seconds, we have the new scaled model with the support automatically regenerated.